Okay, I'm going to get started. So I apologize. I'm going to have to move a little faster. It was great, I think, having questions, but it means that this presentation's longer than I planned. So, okay, so the next kind of performance concern was on the screen here, so I guess he's adjusting. Anyway, I want to first talk about the design of parallel memory architecture a little bit, so you understand why we have these performance characteristics. So when you have a parallel machine, you have many threads trying to access memory. And so in order to not have to buffer those up and make them sequential, we divide the memory into banks so that these banks can all be accessed simultaneously. And this is essential to achieve high bandwidth in a parallel machine. So in general, each bank can service one address request per cycle. And so a memory can service as many simultaneous requests as it has banks. Now, because of that, when multiple threads access the same bank, then you have what's called a bank conflict. And then that's the case where we have to serialize. So the conflicting accesses are serialized. So if we look at some examples here, serialize means that if thread 0 and thread 3 access bank 1, then thread 0 will get its result, and then thread 1 will get its result. I do define this. So, okay, so here's some bank addressing examples. So if we have 16 threads and they each access sequential banks, then this is linear addressing with a stride of 1, then there are no bank conflicts. Similarly, if we have 16 threads and they access a random permutation that's a one-to-one mapping of threads onto banks, then again, there's no conflicts. However, if we have linear addressing but with a stride of 2, then you see that you'll be accessing bank 0, 2, 4, 6, 8, but then 0, 2, 4, 6, 8 again. And so you'll have two-way bank conflicts. And if you have a stride of 8, then you have 8-way bank conflicts. And if you have a random permutation of addresses and you have some random number of threads accessing a given bank, then you have random bank conflicts. Just wait a second. Okay, so it's important to know then how addresses map to banks on G80. Well, G80 has 16 banks, and this is shared memory I'm talking about. And each bank has a bandwidth of 32 bits per 2 clock cycles. And successive 32-bit words are assigned to successive banks. So if you have an array of floats and you have sequential addressing, then each thread can access a different bank. And bank conflicts can only happen within half warps because of the way the warp is split up across the 8 processors. So basically, you compute the bank index from your address in bytes modulo 16. And so you can't have bank conflicts between different half warps, but only within a single half warp. And if you do have bank conflicts, so if you don't have bank conflicts, then shared memory is as fast as registers. It's basically within a single cycle, the threads get their results from shared memory or store their results. And if all threads in a half warp access different banks, there's no bank conflict. And there's another fast case. If all threads of a half warp read the same address, in other words, it's the same bank but also the same address within that bank, then there's no bank conflict. And this is called the broadcast case because we have hardware, so if all threads ask for the same data, then we can just broadcast it to all the threads in a single cycle. And because we figured that, the designers thought that would be a common case where you store something in shared memory and all the threads need to use that single data element. Now, the slow case is where multiple threads in the same half warp access the same bank. And in this case, we have to serialize the accesses. So the cost of a shared memory access with conflicts is the maximum number of simultaneous accesses to a single bank. So in those examples I showed before, with two-way bank conflicts, the cost is going to be twice the cost of access with no bank conflicts. And access with 8-way bank conflicts is 8 times the cost. Yeah, question?
Are the banks meant to represent 1 byte or some like a kilobyte?
There are 32 bits wide, so So basically you have 16 kilobytes of shared memory, and it's divided into 16 1 kilobyte banks.
Fixed banks.
Lars, did you? Fixed banks, yes. Physical bank.
The memory is 16 words wide by 1,000 deep, and each bank is one column. So if you want...
When the allocated is array, it goes across the row, with the banks in the
The linear addresses go across the row of 16 words, and then to the next row, and then to the next row. And then
Yeah.
if you access two things in one column, it takes two reads.
Yeah.
If you access one thing in each column, it's one read. If you access everything, 16...
So if you use floats, there's never an issue.
Well,
It depends on your addressing.
You ask for every even float. It's an issue. Actually,
It comes up. Yeah.
Go back to the previous slide. I think there's that bank address not 16.
Yeah.
Not 16 words. That should actually.
That's true. That's 16 words. So if you have an array of words, like floats, an array of floats or array of ints, then it's the index of that array modulo 16. So, sorry, that wasn't clear. So what Lars explained was that the memory is it's basically two-dimensional. It's 16 columns, and each column is 1 kilobyte. And so if you have an array allocated in shared memory, it's going to go across the columns and then go to the next column and then go to the next column. And so if you're doing sequential addressing of that array across your threads, then you'll never have any bank conflicts. Sequential word addressing. If you stride by 2 or stride by 4, for example, then you're going to have two-way or four-way bank conflicts. Yes?
so then if you have an array of float 4,
Yes.
then it will be more beneficial to actually treat them as floats, as a sequence of floats, and then redistribute them and...
Yeah, this is a case where an array of float 4s, if you just access each thread reads a float 4, it's going to cause four-way bank conflicts.
But you can't access... There's no instruction to shared memory that accesses the float 4.
Oh, that's true. Well, but each access will be one float of the float 4, and the stride will be 4, so it's four-way bank conflicts. So, yeah, if you really want to optimize, I'm going to say something about priorities in a second, then you would actually switch that into 4 arrays of floats.
You can typecast this, well, temporarily typecast this thing into an array of floats.
Right, and then you'd have each thread.
That trick that you showed in the previous
Yes.
exercise.
You could do it. You can do a trick if you have an array of float 4s with a typecast to floats and then have threads read data. But the problem is threads would be reading data that they might not need. And that doesn't help. If you have it in a register for another thread, you can't access it. So just one, yeah, I'll get to that next. What's your question?
So you can have, so basically you're saying that there's parallel access to the banks by each thread of the banks as long as they're columns.
As long as within the group, within a half warp, there are not multiple accesses to a column, then it's fast.
Then it's parallel.
Then it's
Is it
parallel.
parallelized access, or is it just still sequential access?
Across a warp, it's always parallel access. Okay.
Is the 16 by 1K going to change when you go away from half wrap?
Yeah, so in the future, the number of banks may change. I'm not sure if you can query that. So what I want to say about this is bank conflicts, especially low-degree bank conflicts, like just two-way or four-way, like if you're just doing striding every other word, this is the last thing you should optimize. Because often, if it's two-way bank conflicts, it's going to take you twice as many instructions to get rid of that two-way bank conflict, and so it destroys any benefit you got from getting rid of it. If it's 8-way or 16-way bank conflicts, it's often worth spending a few instructions to change or padding. There's some things you can do that don't cost any extra instructions, like if you have, I have an example of this, if you have a 2D array that's a multiple of 16 wide, then you're going to have, if you access columns, then you're going to have 16-way bank conflicts. But if you just pad that out to 17, a multiple of 17 wide, or just add one more element, then you get rid of those bank conflicts, and that doesn't cost any extra instructions. But yeah.
Yeah, one more thing. Does the bank structure apply to global memory or shared memory?
The bank structure is shared memory. Okay. Global memory, the only thing you have to worry about is coalescing. Okay. For shared memory, I would say don't worry about shared memory bank conflicts until last. Yes.
You're talking about access to can you differentiate between read and write at the
It's the same. Reading and writing shared memory obeys the same addressing principles and conflicts and all that. So yeah. Okay, I'm going to go on.
Another question is the read access. You said that the read access cost per register of 11 cycles. That applies to shared memory as well.
There's not a read access cost of 11 cycles. A re-access. Well, there's a pipeline latency for an arithmetic instruction of 11 cycles. Shared memory.
You can issue it every clock cycle.
Yeah.
If you have enough threads. If you only have one thread, you'll feel that 11. If you have one thread.
Yeah. Right. Basically, yeah. Once you have enough threads. Somebody pointed out, and I don't know if this is right. In that slide for covering pipeline latency, it said 192 threads. But if you think about it, it seems like it should be half that.
That's the number I always use.
192?
12 half warps.
12 half warps. Okay. All right. Okay. I'm moving on. So now I'm going to get into actual interesting stuff, some optimization examples. So the first one is matrix transpose. This is an SDK example called transpose, and it illustrates coalescing and avoiding high-degree shared memory bank conflicts. It gets speed-ups for even small matrices. So the idea is you have a matrix, and you want to transpose it. So all the rows become columns. And here's basically the way you would write. In fact, this was the way I wrote my first transpose and then realized how slow it was. So if you basically compute your thread's x index in the array and its y index. And then I have this if here just to make sure I can do arbitrary sized arrays. So we just check if my x index is less than the width of the array and y index is less than the height. If not, then that thread doesn't do anything. And so then I compute an index in from that, which is just my x index times plus the width of the array times my y index. And my output index is just the transpose of that. So it's the y index plus the height of the array times the x index. And then I just read from my input array at index in and write to the output array at index out. Okay, what happens? My reads from memory, if you look at those, index in is always each thread 0 and thread 1 and thread 2 are one element apart. So these are going to be completely sequential. They're aligned. So these reads are coalesced. The stride's 1. What about my writes? Well, now I'm striding across columns, down the columns, across rows of the array and writing with a stride. Each thread, and these two threads are in the same warp. So thread 0 and thread 1 are 16 elements apart if my block of data is 16 wide in this case. And so that's definitely uncoalesced. So what we want to do is utilize shared memory to make sure that those stores are coalesced. So we partition the matrix into square tiles and have a thread block that's dimensions are bx by by. And we read that input tile for each thread block into shared memory. And then we transpose it in shared memory. And then thread txty is going to read an element txty from its input tile and write the element, I guess tx into the output tile. And so then coalescing is going to be achieved as long as the block and tile dimensions are a multiple of 16 for a float array, that is. So what does this look like? So our reads, we read from gmem and then write to shared mem. And of course this is coalesced as it was before, and we write sequentially. But then we do our striding across rows in shared memory rather than global memory, and then write coalesced to global memory. So we write linear addresses into global memory. And there's one more optimization, and that's that in shared memory, when we were striding across these rows, well, our block was 16 by 16 floats. And so when we stride, thread 0 is going to access bank 0, thread 1 is going to access bank 0, thread 2 is going to access bank 0, etc. So we're getting 16-way bank conflicts. And that's just because our 2D array in shared memory is 16 wide. So we can get rid of that just by adding an extra column. We can just pad that array. Really simple. And then our read stride becomes 17, which means that thread 0 is going to access bank 0, Thread 1 is going to access bank 17 modulo 16 is 1, bank 2, bank 3, etc. So threads are consecutive. There's no bank conflicts. Now, earlier I said don't optimize bank conflicts until last. In fact, we did this last. This optimization, I think, isn't in the CUDA 1.0 SDK. It's in the CUDA 1.1 SDK. But this was a free optimization. All we did was spend a little bit of shared memory, and we were optimizing a really high degree bank conflict. It's not a two-way bank conflict. It's a 16-way bank conflict. So this makes a big performance difference. I'll show you that in a second. So what's the code look like? Well, it's more complex, but it's worth it. So here we allocate our shared memory array, and notice that it's blockdim plus 1 times blockdim. That's how we pad it. And then this is actually using these intrinsics, but ignore that. Those are just multiplies. And we compute our block index, x and y, and our index within that block, which is x block plus thread index, and y block plus thread index dot y. And then if we're inside the array, then we compute our index in and our index out as before, so width times y index plus x index. And then the index block is now thread index dot y times the width of the array in shared memory, which is blockdim plus 1, plus thread index dot x. And so now we read from index in the input array, but we write into block, which is shared memory, at index block. And so all the threads are going to read each thread is going to read its element into there. And then we compute a transposed address and an output index. And so notice that after we do that, we have to synchronize. So we sync threads now because threads are transposing in shared memory, but the thread isn't going to write out to global memory the thread that it transposed, or the data that it transposed. And so we have to synchronize so that the data is up to date in shared memory. And then we just write out from the transpose index in the block to the output index in the output array. There's one other thing to notice here. We have to evaluate this condition twice. The reason for that is you can't sync inside a divergent branch. And because if you think about it, sync threads waits for all threads in a block to reach it. And so if we put the sync threads in here, then the threads that are outside of the dimensions of the array, you're going to be waiting forever for those and you get deadlock. So you can't sync inside a block. Yes?
So you use this mul24 instead of ignore it.
Yeah, I'll talk about it now. Yeah, so the reason for using mul24, the multiplier on G80 is 24 bits wide, not 32 bits wide. But the compiler for a star multiply operator for integers generates a 32-bit multiply, which takes, I think, six instructions, something like that. 4, somebody said? Yeah, so anyway, this is, on G80 is faster. The bad thing about using this is that on future GPUs, when we actually build a 32-bit wide multiplier, emulating the mul24 is going to take more instructions. So I would actually only use it if it gives you a significant performance increase, which I guess it did for this example. Yeah, oh, I don't know. Sorry. We don't have measurements for that in this. But I can tell about the speedups with the coalescing and shared memory. So if at the bottom, this is just doing the coalescing optimization without the padding in the shared memory array. And you can see that this, well, actually, I guess I have to talk about it. So originally, it was for, say, a 1024 by 2048 array. Without coalescing, it took 6.6 milliseconds. With coalescing and the shared memory optimization, it's 0.79 milliseconds, so it's a factor of 8.4. So it's almost the factor of 10 that you get for raw coalescing, but since there's some other work to do, it wasn't a factor of 10 originally for the slowdown of non-coalesced. Now this is without the padding in the shared memory array, and you can see that it's a little bit faster to optimize those bank conflicts. So it's, I don't know, maybe 10%. Yeah, it's not really that much.
10% for a 16-way?
Yeah.
It's not worth it.
Right. So, well, but it was free. It didn't add make the code that much more complex.
A lot of people run into shared memory limitations. So.
Yeah, that's true. Yeah, that's true. If you're trading off amount of shared memory for bank conflicts, err on the side of the amount of shared memory because you probably need it, and it's going to reduce your occupancy, stuff like that. So yeah, Lars is right. This is sort of a micro optimization. It's only 10%. And that's why I say leave bank conflicts for last. Okay. Any questions on transpose anymore before I go on? Okay, so now I'm going to talk about optimizing parallel reduction. Okay, so I already talked about what a parallel reduction is yesterday, or this morning. No, that was yesterday. And a basic parallel reduction is pretty easy to implement in CUDA, but as you'll see, there's a number of optimizations that you can do to get higher performance. So I'm going to walk through 7 different versions. Am I doing it on time? And demonstrate 7 different optimization strategies. So yeah. In fact, I might skip really fast through the first 2 because they're probably mistakes you wouldn't make in the first place. Okay, so we're doing a tree-based reduction, which means we're basically using log n steps to sum the values. But we want to do, in this case, really large array. So I want a computer reduction for 1 million elements or something like that. Which means I'm going to have to partition it across multiple thread blocks in order to keep the GPU busy and to process very large arrays. So I divide it up into blocks where each thread block reduces a portion of the array. But the question is, how do we communicate the partial results between the thread blocks? Well, if we had a global synchronization across all the thread blocks, we could easily reduce this, without stopping. But that global sync would be expensive to build in hardware, and it would force you to run fewer blocks, basically no more than the number of multiprocessors times the number of blocks you can have on each multiprocessor. Otherwise, you'd get deadlock if you did a global synchronization, because those blocks wouldn't be active on the GPU, so they'd never hit their synchronization. So instead, what we do is we use kernel launches as synchronization points. So we run a kernel to do a summation of each block, and so then we get a partial sum in each block, and then we write that partial sum out to an array, and we do another level and reduce, and we can actually do multiple levels like this. And so each of these different bands is a kernel invocation. Of course, but they run the same code, so we don't have to do multiple different kernels. Okay, so now we want to optimize this. So when you start to optimize something, John Stone mentioned this yesterday, you want to know what your optimization goal is. And so you should strive to reach GPU peak performance, but that requires choosing the right metric. So if you know that you're compute bound and not bandwidth bound, then you want to optimize for gigaflops per second. If you know you're bandwidth bound, then you want to optimize for gigabytes per second. In some algorithms, you're going to have a bit of both, and so you want to look at both metrics. In this case, reductions have extremely low arithmetic intensity, and so they basically do one floating point operation per element that's loaded, and that's if you're bandwidth optimal, which means you don't load elements more than once. So that means that we need to strive for peak bandwidth. So if I use the G80, the 8800 GTX, for example, in this example, it has 86.4 gigabytes per second. So that's my target. Okay, so I'm actually going to skip to optimizations because, to be honest, I didn't make these mistakes in my first version. I just kind of did them to see what the difference would be. But here's what our reduction looks like when we start. So the way we're doing it is we're folding basically the array in half at each step and adding together the elements that line up, right? So each thread reads its element and the element n over 2 elements away, and then you divide that stride by 2, and each thread, there's half as many threads, each thread reads its element plus n over 4 away, plus n over 8 away, etc., until you've got a single value. And by doing it this way, rather than the other case was interleaved addressing, where you start with a stride of 1 and you go up by 2 each time, then your accesses are all sequential. So we start out with a good base, and our performance is this, 9.7 gigabytes per second. Well, that's not very good. This is for 4 million element reduction. 9.7 gigabytes per second is, you know, an eighth or a ninth of the bandwidth on a G80. So here's a problem. If we look at the code, I should show you the code, the original code to start, sorry. So here's the original code where we have this reduce, and each thread computes an index into the whole array. It loads that into shared memory, and then it synchronizes. And then there's the reduction loop in shared memory. So we basically just change our stride at each step by a factor of 2, and then access an element and an element, stride elements away, and add them together and synchronize each time through the loop. And then when we get to the end, we have a single result, so only one thread needs to be active. So we say, if my thread ID is 0, then I write the answer out to my block index. And that way, on the recursive call, you know, you can load from your block index to do the next level of the reduction. But now the code looks slightly different now. We now have this, the loop is actually like this for the kind of sequential accesses. We start with the stride is blockdim.x divided by 2. And if our thread ID is less than the stride, then we do the add. Well, the problem with this is that on the first iteration, half the threads are idle, because we start out with s as blockdimension.x divided by 2, and there's blockdim.x threads. So what can we do to make those threads more useful? Well, let's have each block sum twice as many elements. So we have the number of threads, number of blocks, and replace the single load at the beginning with 2 loads. So now, notice we changed the threads index to have a stride of twice as much, or the block index times twice the size, and then we load 2 values, gi data I and gi data I plus blockdim.x, and add them together. So we do that. We do the first add while we're loading, basically, and that's simple, but it at least makes the threads more useful, and that basically gives us 1.8x speed up. So we're up to 17 gigabytes per second. Okay, but at 17 gigabytes per second, we're far from bandwidth bound yet, which is our target. So what's the likely bottleneck? Well, it's probably instruction overhead, because we're not compute bound and we're not bandwidth bound. So what else can it be? Well, we're probably maxing out our instruction issue rate, but without doing useful work. So where do those instructions come from? Well, they come from address arithmetic and loop overhead. So the next thing I'm going to do is unroll the loops.
Sorry, can you back up a second?
Yeah.
I don't understand this trying to be bandwidth. What bandwidth do we want to be bound by?
We want to hit the peak efficiency of the machine. So the question is, why do we want to be bandwidth bound?
So what bandwidth are you referring to?
Oh, the device memory bandwidth.
Device what?
Device memory bandwidth. The bandwidth between the GPU and the memory on the card. Right?
Okay, so this is the device global memory.
Global memory bandwidth, yes.
Share or local.
Right, yes. So that's 86.4 gigabytes per second, and we're only at 17. So we probably have too many instructions per add in the reduction. So we have a lot of overhead. Well, we can reduce that by unrolling. Lars showed unrolling for n-body, where he just unrolled by a factor of 4. But in this case, we're going to try to unroll as much as possible. And one observation is that as the reduction proceeds, the number of active threads decreases. And when the stride gets below 32, you only have 1 warp of threads left. And within a warp, instructions are sim-desynchronous. And what that means is that all threads get their results at the same time, and all threads update shared memory at the same time, which means that we don't need sync threads. So within the last warp, we don't need sync threads. And so we can unroll the last 6 iterations of the inner loop and completely get rid of the sync threads there. So what we do is our loop, we just stop when s is less than or equal to 32, and then we have the final branch, that if TID is less than 32, then we do the last 6 adds, and we just hard code the stride, 32, 16, 8, 4, 2, 1. And so this is basically the optimal instructions for doing a 32 data element reduction. And the thing to note is that this saves useless work in all the warps, because even though only one warp was active in the last iteration of the loop, all of the warps computed the loop condition, computed the branch to figure out if they were less than 32, etc. But now, once we compute if TID is less than 32, there's only one warp active. Okay, so that gives another speed up of 1.8x, so we're up to 31 gigabytes per second. And can we unroll completely? Well, if we knew the number of iterations of the loop at compile time, we could completely unroll the reduction. Well, luckily we do know at least the maximum size, because we know that we can launch at most 512 threads. And we're sticking to power of 2 reductions here, power of 2 block sizes. So we can easily unroll for a fixed block size, but we need to be generic. We need to be able to support 128 threads, 256 threads, etc. So how do we do that? Well, it turns out you can use C++ templates to do this, because CUDA supports templates on device functions. So what we can do is we can pass the block size to the kernel via a template parameter. And you might think, well, why would I do that? Because you automatically get block size in blockdim.x, but you don't get that at compile time. In this case, we're going to tell the compiler, or we're going to give the compiler this data. So we're going to say the block size is a template parameter, and then we can just unroll that loop and just say, you know, there's only 3 more iterations. So we just say, well, if the block size is greater than or equal to 512, we need to do the 256 iteration. And if it's greater than or equal to 256, we need to do the 128 iteration, etc. And this may look like it's a bunch more branches, but actually all the code in red is evaluated at compile time because it's templates. So it all goes away in your compiled code. And so this results in basically a perfectly efficient reduction for block sizes up to 512. And, well, the question is, don't we still need to know the block size at compile time in order to do this? Because template compilation will fail if you try to invoke it with a runtime parameter. Well, in our host code, all we do is we hide this away in some library routine for reductions. But all you do is you switch on the number of threads, and then you hard code the template parameter to all the possible block sizes. And there's only 10 of those in this case. So for some algorithms, obviously, this isn't going to be feasible. But for something like a reduction, this works quite well. You still, at some point, need to know what size. And if at runtime you're determining your block size, then you have to have this switch somewhere. All right? If you know ahead of time that you're always going to be reducing 128, then all you need is this. Right? Yeah. But if you want to write a library that can support multiple block sizes, then that's what I was doing. Anyway, so what's the speed up here? Well, this is another 40%. Since this is only the last 3 iterations we're unrolling. And in fact, since my block size was 128, it's just one more, but it gets rid of the loop overhead. So we're up to 44 gigabytes per second. Okay, last one. Now, and this is probably the wrong order to do this, but this was the order I thought about it and did it. But really, we should have optimized algorithmically first. And this takes a little bit of thought about complexity. So this is the slide I showed yesterday. I showed that the time complexity of the reduction is order n over p plus log n, right? Well, there's another thing to consider, and that's the cost. So the cost of a parallel algorithm is processors times time complexity. In this case, they're threads, but I'm going to think about them as processors just to simplify it. So think of it as a connection machine. You've got as many processors as you have threads. So if we allocate threads, within one block, the time complexity is order log n, but we're using order n threads, and so therefore our cost is order n log n. And the cost of a sequential algorithm is order n, and so we're not cost efficient. Well, Brent's theorem suggests that there does exist, and I'm not going to go into the details of Brent's theorem, you can look it up, but that if you use order n over log n threads, then there exists an algorithm that is cost order n. And so basically what you do is you have each thread do order log n sequential work instead of order 1 sequential work, or order 1 work. And then all order n over log n threads cooperate for log n steps, and that works out to n over log n times log n, which is order n. And so this is sometimes called algorithm cascading, because what you do is you do some sequential work in each thread, followed by the parallel tree-based work to do the final reduction, and that can lead to significant speed ups. So I guess, so you combine the sequential and parallel reduction, and Brent's theorem says that each thread should do order log n elements. Well, it's not exactly the same here because we have threads instead of processors, and they share the processors, and there's memory latency and all this stuff. So in my experience, it's beneficial to push it further and do much more than log n elements per thread. And on G80, through experimentation, I found that I got best performance with 64 to 256 blocks of 128 threads, and for, say, 4 million to 8 million elements, or 60 million elements, that means you're doing 1,000 to 4,096 elements per thread. So what do we do? Well, all we do is we replace that load and add of 2 elements at the beginning that I talked about, which is basically sort of the first step of this, with a loop. And I just have each thread load and add a bunch of data sequentially. So while I is less than n, I add element I and I plus block size, and then I increment I by the grid size. So basically I size my grid so that it's much less than the number of elements, and then I just iterate and do another block, etc. And then when I'm done with all the sequential work, I synchronize and do my tree-based reduction within shared memory the same way I did before. So the grid size loop stride ensures that all the threads are sequential within each iteration of the loop so that you're coalescing. And how does that help? Well, that's another 40% increase, and we're up to almost 63 gigabytes per second for this last kernel. And if you run even more elements, so basically if I ran it on 32 million elements, and I think even 16 million elements hits this, and got 72 gigabytes per second. And that's out of 86, so that I felt that was pretty efficient and far enough to go. But I suppose you might be able to do other stuff with that new loop and optimize it further, but I doubt it. It would get much faster. Yeah?
Didn't you do any experiments like this with sizes which is not for the power end, but with conditions?
Not on the reduction. I haven't done non-power of 2 sizes yet, but I have done non-power of 2 sizes for scan. And basically, all I do is have a fixed block size, and then when you initialize the block, you write zeros into the last block beyond the limit of the array. So you're always, it doesn't affect performance that much. So, yes?
So this may be a question that reveals some ignorance, but, and I understand that this is an example that shows how this particular, it's not really to show us how reductions work, but how to do the optimization.
Yeah.
My question is, so in the MPI world, all the specific things like reductions are under the hood and it's a simple call.
Yep.
How much of that is already available?
That's actually a personal project of mine. We don't have any standard data parallel library that's made by NVIDIA. Well, not officially as part of CUDA, but I've been working with, I talked about it yesterday, the CUDA library with the guys at UC Davis. And so our goal is to have all this kind of stuff available. And we want to have it at multiple levels. So at an application level, so if you really do just need to add up a bunch of values, you can just call reduce at your application level. And also at the kernel level. So there's kernel routines that you can include and call, just reduce within this block, for example, or across these threads. And so that's the goal with CUDA. It doesn't have the reduction stuff yet because we were focused on scan as a research project. But the next release, I plan to put this stuff in it, for example. And hopefully, it'll be open source, so hopefully that'll grow organically with other contributors. Yeah, we're at time. Dave needs to go. So can we save questions for, is it a quick question?
Yes, real quick
Okay.
question. Of the optimizations that you've done, are they all independent, so you can do one and not the other?
Yeah, I think most of these are pretty independent. I didn't try them in different orders or different combinations. It'd be interesting to see which ones are most important. You can kind of see the ones that get bigger speed ups than others. But then again, I think the algorithmic one would actually give a much bigger speed up if you did that at the beginning than at the end when you were already closer to 50% of the bandwidth, for example. Okay, there's a graph of the performance and for different numbers of elements. But so the point to see here is that most of the biggest speed up total came from the algorithmic optimizations versus the code optimizations. So really you should do the algorithmic ones, things to maximize parallelism first, and then optimize code with loop unrolling and stuff like that later. Okay. Okay. Oh, you plug in? No, I can't. You need the cable. You need this.